Good morning, everybody, and welcome to the YouTube folks, and welcome to the 268 of you who've just come to the room in real time. It's always good to see people in real time, I think. Although certainly the majority of the class is not here. You're here, and that's what's important. Let me share my screen. Where is it here? Go down to screen 2 and see what's going on. What we got is we're going into chapter 10. That was supposed to be an animation. Make sure my chat window is going here. Chat and participants. Good. Okay. Getting into period and frequency, and I'm going to start talking about simple harmonic motion. Oh, there it is. Simple harmonic motion is just mass on a spring going back and forth. It's the basic idea. And there's lots of examples actually of simple harmonic motion in real life, not just of an ideal mass on a spring. So these markers just finished up marking. I just tried posting this like literally 5 minutes ago before I came in here. So these are fresh off the presses. Average 72%. These are sort of the breakdown. Basically, take a look over the marking. Also, take a look at the rubric, which has detailed marking instructions that were given to your TA. It's called Midterm 4 Written Solutions with Grading Instructions. Take a compare it. Remember that for each problem, one TA marked the entire class and made certain decisions. The TAs were consistent, I hope, and stuck very strictly to this 2 + 2 + 2 + 2 rubric. So part marks were deducted the same way for every student in the class. If there was a mistake in your marking or in the computation of your mark, I would like to fix that. I'll just remark your test. It's very easy to do. I just click on the link and go back to CrowdMark and take a look. All you have to do, send me an email to physics131fall at physics.utoronto.ca. Let me know there's a mistake and let me know that you request a remark, basically. If you do this by Monday, November 30th, then on December 1st, what I'll do is I'll look over all those requests and get it remarked. So I'm going to be doing the one remarking. Please don't contact the TAs because they're done their little contract. I want to do a quick poll here. It's going to be based on a demo, which we might as well do. Solid disk is released from rest and rolls without slipping down an incline. A hoop with the same mass and radius does the same. Which reaches the bottom with a greater speed? Is it, where's my polls here? A, the solid disk, B, the hoop, or C, both reach the bottom with the same speed? Looking at these results coming in, it's what they call 50-50-50 so far. Actually 34. I know it's a little hard to think it's first thing in the morning here, but let's give it a try. So try to click in your best guess for this one. Give you another 10 seconds. We're going to try to actually do it. Okay. Let's end polling. Sharing results. So it was 37% voted for the disk gets there, goes faster. 31% think the hoop goes faster, and 34% think that they have the same speed. So luckily nature is not a democracy. It's a it's the dictatorship of Mother Nature, right? So why don't we stop the share and actually try this out? I'm going to try a different microphone. Okay, everybody, I hope you can hear me. I'll try to speak kind of loudly. I actually happen to have a disc and a hoop. So I've got a solid disc. It's made of wood, and the hoop is made out of metal. They've been machined so that they're actually the same mass, and they're even the same diameter. Everything is the same about them except the mass of the hoop. It's all concentrated at the edge. It's made of metal, whereas the solid disc, it's all spread out throughout. So what I'm going to do is, well, I'm just going to release them both from rest, right? I'm going to put the disc in front and say, on your marks, get set, go. Okay, did you see that? The disc won. We can do it one more time. We'll put the disc behind the hoop in front. It goes faster, gets there faster, and the disc arrives at the bottom with a greater speed than the hoop. Screen 2. Okay. Get my Zoom ducks in a row here. Okay. So the answer is it's the disc. And we can actually do an example of this one to try to solve through how it actually works. It is a solid disc, or say a hoop, one or the other, starts from rest and rolls without slipping down an incline. The change in height is h. So it goes this distance, h, down the incline like this, starts at the top, the initial, V initial equals 0, and then comes down here to final. V final is question mark, okay? The radius and mass are not given, although they seem like they're important. Not given. Maybe they're not important. We're going to do rolling without slipping. So there's a constraint there, right? It's coming from the static friction, which is that V is equal to omega times R. And so I guess omega final is going to be equal to V final divided by the radius. There's also going to be rotational inertia. And what I'm going to do for rotational inertia is I'm going to actually say that it's I is equal to C times mr squared, where if it's the solid disk, then you got C equals a half. And for the hoop, C equals 1. It's some dimensionless number, which you'd get from that table in your book. Okay, so what we're going to do is define the system. Is the object plus Earth. So that I'll use the gravitational potential energy. Assume no external work done. The static friction doesn't do work. So what it looks like is that the kinetic initial plus the rotational kinetic initial plus the UG initial plus the work is equal to the kinetic final plus the kinetic rotational final plus UG final plus the, any change in internal energy. So what I'm going to do is say that it's just 0 plus 0 because it starts from rest plus all of this energy. I can maybe put it in 4 ticky things or something, is in the MGH equals, and there's no work done. What we're going to do is now split that up so that there'll be some linear kinetic energy and some rotational kinetic energy. So that So that's how these bar graphs work with this problem. And the way you represent it mathematically, 0 plus 0 plus mgh is the initial potential, plus 0. And Nisa, yeah, I would give you the C value on a test, or you could look it up pretty easily, but yeah, I don't think I'm gonna force you to look it up. So it's 1/2 mv final squared plus 1/2 I omega final squared plus 0, because it ends up with 0 height plus, and there's no change in internal energy. So this so just rearranging it, you got mgh is equal to 1/2 m times v final squared plus 1/2 I times omega final squared. And what we're going to do is just plug in that I is equal to cmr squared, and that omega final is equal to v final divided by r. So it's mgh is equal to 1/2 m times v final squared plus 1/2 times c times m times r squared times v final over r squared. Okay, and the m's cancel, which is good because you weren't given the masses of either, so didn't want that. So you've just got GH is equal to V final squared over 2 plus, there's a C, there's an R squared, there's a V final squared over 2R squared. Now the R's cancel, that's good. Actually, so there's no more R's either. And since we didn't know the radius or the mass, it's good that they're not there. I can times both sides by 2. I get 2 times G times H is equal to V final squared plus C times V final squared. So it's actually equal to 1 plus C times V final squared. So V final is equal to the square root of 2GH divided by 1 plus C. So for the solid disk, V final is equal to the square root of 2GH over 1.5. And so for the hoop, it's V final equals the square root of 2GH over 2. So disk goes faster. So Furtis on the chat asked a really good question. He says, if it's rolling without slipping, doesn't it mean there's friction? Yes. And if there's friction, wouldn't there be a change in internal energy due to this? No. And the answer is, the reason is that this work due to friction, or this change in internal energy due to friction, is for kinetic friction only. With rolling out without slipping, it's static friction. So static friction does no work. I'm going to put that in red because it's an excellent, excellent point. Static friction of stationary surface does no work. Hopefully that's not too messy. And I've just decided to use, energy as opposed to kinematics. You could do the same question with kinematics and get a similar answer there. But that's the reason, I like to think of it in terms of energy. That's the reason that the solid disk goes faster. And there will be some kind of question like this on your midterm 5 that's coming up on Tuesday. So it's a good one to know. And again, rolling without slipping means that the bottom of the thing is stationary. So it's got static friction. And you've got this rolling without slipping constraint. Yeah, we should move on. 1124. Move on to chapter 10. So we've been studying linear motion, objects that move in a straight line at either constant velocity or constant acceleration. We've also studied objects that are rotating or moving at a constant speed in a circle. In this chapter, we're encountering a new type of motion in which an object vibrates back and forth. If you go to the My Lab and Mastering, just quickly, I'll let you know there's a homework 10, which is due on Monday, or it should do it on the weekend, really. Also, I've posted an item that's not for homework credits called Videos and Practice for Chapter 10, which you can check out if you want. It's got 4 of these nice, like Khan Academy style videos that Pearson does, which I think are great. Mass and the Spring, Conceptual and Quantitative, Pendulum, Conceptual and Quantitative. I think they're good to work through. The other video they have, which is kind of fun, is an experiment in which this girl actually hooks up an experiment, takes a mass hanging from a spring, cuts it, and then you can make some measurements and go through these things. When you actually see it, I think it's helpful. And it's fun to listen to the chatter in the background because it sounds like these are real students. I want to mention, this is just about period and frequency and how they're related. This is how the chapter starts out. So if you have position versus time, sometimes it goes and repeats. So it might go up, down, up, down. It might go in a triangle. It might be something that's a very complicated pattern, but every time it repeats, repeating motion at a certain period has a period. So all these motions have a period. Which is called capital T in seconds. Units of period is seconds. And here's a video. Here is a video of something that's not sinusoidal. There might be sound in this one. Let's see. So it's filling up with water. And when the water gets high enough, it should tip. And then it fills up again. So this is periodic motion, but it's not sinusoidal. It sits there for a long, long time, then goes dunka, and then comes back up. Let's go to the next slide here. I'll go to the next slide. Maybe this one. Okay, so the time to complete one full cycle or one oscillation is called the period. The frequency, F is the number of cycles per second, and you relate period and frequency by this 1/over. So frequency is 1/over the period, and also the period is 1/over the frequency. The frequency has a new unit, which is called hertz, and hertz is just 1/over seconds, sorry. Cycles per second, or hertz. Sometimes you also see it called HZ for short. And a couple of polls. If we turned up the water flow of that fountain and we doubled the frequency, how would it change the period? Relaunch polling. Is it A, the period is also doubled? B, the period is reduced to half of what it was? C, the period is unchanged, but the fountain tips twice as far? Or D, the period is unchanged, but the fountain tips half as far? That was a peaceful video, wasn't it? Hopefully it eventually moved for you. There wasn't a lot of motion. Okay, 10 seconds for this poll question. Review. Three, two, one. Okay, 90% of you got exact. That's the idea. is at the period. The period t is equal to 1 over the frequency f. So if the frequency goes up, that means the period goes down. Let's do a more kind of quantitative thing. If you've got a pendulum, like this one, which has a period of 2 seconds, that's how long it takes to swing all the way back and forth. So it starts at one end, takes 1 second to swing all the way across, and another second to get all the way back to where it started. What is the frequency? Is it A, 0.50 hertz, B, 1.0 hertz, C, 2.0 hertz, D, 4.0 hertz? Just getting used to these equations. Another 10 seconds. They come up a lot in the Master in Physics homework, I found. So it's good to be familiar with them. 2, 1, 0. Yeah, 0.5. Exactly. So 88% of you got that it's, sorry. The frequency is equal to 1 over 2. Okay. And it's 1 over 2 seconds is equal to 0.5 hertz. That's how the units look. Okay. So this is sort of the canonical, the starting place for a lot of studies of simple harmonic motion, which is you consider an ideal mass sitting on a frictionless surface, and it's attached to a spring. And the other end of the spring is attached to a fixed wall. And so if you stretch the spring by pulling the mass and then release it, when the spring goes back to where it started, sort of an equilibrium where it's not pushing or pulling, will the mass be moving at that moment? And the answer is that yes. When it gets back to equilibrium, it's not accelerating at that point, but it is moving. And so it's got some velocity. It'll have sort of negative velocity when it gets back to equilibrium. So it'll have its own inertia, which will cause it to overshoot the equilibrium and go to the other side. It will always cause the spring to compress. So again, once again, the idea is you take this mass in the spring, you pull it away from its equilibrium, release it, and let it go back to equilibrium. It'll get to equilibrium, but it'll be moving at that point, so it'll overshoot equilibrium, compressing the spring, and have it pushed back to equilibrium. It'll turn around, and it'll reach that equilibrium position again, and then to overshoot it again. So that's what keeps on happening. So equilibrium is the position at which a vibrating object resides when it's not disturbed. If you're at rest at that position, then there's zero forces. The sum of the forces is zero net force. So it just sits there. If you are in motion, then the object always overshoots that position. So if it's moving, it's got negative velocity, then it goes from positive to negative, from the plus side of equilibrium to the negative side of equilibrium. If it's going with positive velocity, then it's going from the negative side to the positive side. So it's flipping its sign of its position. Another word that comes up a lot in chapter 10 is restoring force. So when an object is displaced from equilibrium and there's a force on it that's opposite the direction that it's displaced, then this is called a restoring force. And an example for that is the spring. If you stretch the spring to the right, sorry, to the left, then you have a force to the right, which will be pulling it back. If you compress the spring towards the right, then it'll push it back towards the left. So here it is. So I've done it a little bit opposite here. So the restoring force that we have is called Hooke's law for springs. It's F equals Kx, where K, just mention here, K is the spring constant. Units are newtons per meter. Okay, it tells you how stiff the spring is. And X is the displacement away from equilibrium. So X equals 0 at equilibrium. Okay, so that's, you've also got, if this is the only force, if there's 0 friction, so no friction, then the sum of the forces, horizontal forces, is going to give you, I guess, Fx or something. Okay. This is also Fx. So you can just combine these two equations and solve for the acceleration. You get the acceleration is equal to negative k over m times x. Okay. I got some questions coming in on the chat. So if friction's negligible, there's no outside forces, wouldn't it overshoot and move forever? Yes. So simple harmonic motion does go on forever. The force is always trying to restore it to equilibrium. That's right. It's always bringing it back, always pushing towards x equals 0. And also the midterm 5 is going to be just multiple choice again on Tuesday. Okay. Now this looks like a simple equation. Acceleration is negative k over m times x. Unfortunately, it's not. It's really kind of tricky to solve. So remember, acceleration is the rate of change of velocity, and velocity is the rate of change of x. So what this equation is saying to us is that the slope of x is some negative constant, k over m, because k and m are both positive, times x. This is a second order differential equation, and there's just no easy way to solve it, I'm afraid. It's a weird thing. You're not going to use your equations of constant acceleration, for example, because it's not constant acceleration. So all that kinematic stuff that we learned back in chapters 2 and 3 and stuff and started using it, you can't use that here. That's why we're way up in chapter 10. So k is a positive value, right? K and m are both positive, and so negative k over m. The reason the negative sign is there is because the force is in the opposite direction as the x. You pull it to the right, the force is to the left. If you push it to the left, the force is to the right. That's what the negative sign means. Julianne asked a good question on chat. Oh, and there's the hand. My hands are not showing here. So scroll. Oh, it's down. Nobody wants to talk today. So what are we going to do? Well, I got an idea. So kinematics won't work, or will it? Let's try a thing called numerical integration. This is a trick where you split up the motion into many segments, each over a small time delta t, in which things that are not constant are almost constant. Anything's constant if you look at it for a short enough amount of time, right? So if the acceleration is almost constant over a small time delta t, like 1/100th of a second, then you can estimate like an updated new velocity after that small time with just this kinematics equation. You can just say the new velocity equals the old velocity plus a times delta t. And if the velocity is kind of almost constant over delta t, then you can update the position as well. The new position is the old position plus v times delta t. And what you could do is just step through the motion, one by bit by bit by bit. This might take you like thousands of tries, like steps to do it. But if you have a computer, then you can just do it on a computer. And so what I want to do is open up a Google spreadsheet, not an Excel, as we'll do it on Google Sheets, if you want. You can follow along. I put the link to it here somewhere. So the things that are in pink, I'm just going to say are going to be input values. So I'm going to start at time is 0. And I'm going to start at x equals, I'm going to actually start at x equals 1 meter. That's what she does in Epkina, but with 0 velocity. And for a time step, let's choose something small, like 100th of a second, 0.01 seconds. And for K, we might as well just put 1 Newton per meter. I'm just going to put ones and things because it's kind of easy, and 1 kilogram. So we've got a 1 kilogram mass attached to 1 Newton per meter spring. It's oscillating back and forth. And now I'm going to compute all this stuff. So also we need to do this Hooke's law. So what I'm going to say is acceleration is equal to -1 times the spring constant K divided by, oops, it should be Kx times m, right? Let's do this right. This should say K times x divided by m. So let's do it again. It's going to be -1 times the spring constant K times the x value, which is 1 meter right now, divided by the mass m. And now I'm going to be doing some cutting and pasting. So there's a trick when you cut and paste. If you don't want it to update it automatically, you got to put $signs around the letters. So the F's I'm going to put $signs around because I want it to just keep that. But I'm always going to use the position from the row that I'm in. So I'm not going to put $signs around the B2. Acceleration is -1 meter per second. Okay. So then time, I'm going to say time is equal to whatever the time was plus my time step. And don't forget to put the $signs around the F's so that they don't update when I'm doing my Control C, Control V. We're following here? And then x, so I'm going to use this equation over here. The new x is equal to the old x, so it's equals to the old x plus, open a bracket. I don't have a speed yet, so let me just use the old speed. That might not be a great thing to do, but it's better than nothing. It's probably, everything's roughly constant, right? Times your dt. And don't forget to put your reference values there and your F's and $signs so that it doesn't update on the Control C, Control V. And then the velocity, the new velocity is equal to the old velocity plus A, so I'll just use the old acceleration times your dt. Simple, 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 simple stuff. There's no tricks up my sleeve. That's why I'm showing you all this stuff. Don't forget the $signs around the F. And we can update the A by just Control C, Control V. So that's it. It doesn't look very interesting yet, but what we can do is take these 4, 1, 2, 3, 4, Control C all of them, and then I'll just scroll down to the bottom of this thing, press Shift, and then Control V. And so it just does it again and again and again. So you can see what it did here for time. It smartly said, oh, it's A3 plus F2. And then this one is A4 plus F2. So just added up the times step by step. For X, it did B3 plus C3. So it grabbed the old velocity and just updated it. Again, I'm not sure it's such a great idea to use the old velocity each time, but that's what I did. And then these, so you can see the C's and the D's all go up bit by bit, acceleration. So it's weird. So, okay, so what does it look like? Well, why don't we make a chart? So you can go on here and press Insert Chart. Oh my God. Okay, so this kind of stuff, honestly, sends a chill up my spine. It's cosine. Look at it. It's beautiful. And not only that, look at the time axis. So cosine starts at +1 at 0. Where does it go down to -1? Well, we can actually see. Let's go to the actual chart here. or to the actual numbers, where does this get to a negative 1x, or as far negative as it's going to go? Oh, it's already back. It got to as negative as it overshot 1 a little bit, but it got to as negative as it's going to go, somewhere between 3.14 and 3.15. It's pi. I mean, this kind of stuff, this is why I like physics, I guess. My mind is completely blown by this. Somehow, okay, so what's cos? Remember SOHCAHTOA? Cosine is supposed to be adjacent over hypotenuse of a triangle. So where's the triangle here? This is a mass on a spring. Look at what I've done. All I've done is done a stupid kinematics problem with Hooke's law. There's no triangle. There's no circular motion. So I don't know where pi came from. I thought pi was supposed to be the ratio of the diameter to, or circumference to the diameter of a circle. And yet here it is. I've accidentally computed pi. And if I change this time step to be 0.0001, I will compute pi to 5 digits, right? It just gets, and I've done this, your spreadsheet gets longer and longer. I don't know if the Google Sheet will go up to tens of thousands, but you can compute pi this way. It's just mind-boggling. Now, it's not perfect. It does sort of overshoot there, and that's because I did some kind of kludgy things in this numerical integration. But again, all you have to do to get it better is just reduce the time step. So it's a cool thing. And what's weird is that I honestly don't even know why it works. Like, here's this equation. It's a second order differential equation. What's the solution? Well, if you go to math class, which you do, which I did, I remember this. I remember this very, very clearly. There was d by dt, d squared by t squared of x equals negative a constant times x. And at that point, the professor turned around, looked at the class and said, we will do a trial solution. And there's the trial solution. And then he plugged the trial solution into the thing, and it all worked out beautifully. And I raised my hand. I said, sir, where did the trial solution come from? And he said, doesn't matter where it came from, it works. And he showed that it works. So it's a guess, basically, and it works. It's cosine. And clearly it is cosine if you do the Excel spreadsheet. So, it's something about the beauty of math or physics or something. Anyway, there it is. It's right out of your book. So, okay, so what's interesting about this is that x equals plus a at t equals 0. Now, what is t equals 0? T equals 0 is just where you happen to start the stopwatch. So that's kind of arbitrary. You could have done it at a different place. So if the object is like at x equals 0 at t equals 0, you could use you could actually use sine. So Edkina puts in here, so sine and cos are actually the same curve. They're just displaced by this pi over 2. So sometimes you'll see books use sine. I usually use cos. We're getting one here. So this is called simple harmonic motion. Simple harmonic motion is motion that can be described by this following equation. That's a mathematical model of the motion. And we can try to graph what it sort of looks like. There's the sine curve. There's the period, t. So what goes on here is that you've got F is equal to negative k times x. You got the acceleration is the net force divided by the mass. So the acceleration in the x direction is negative something, k over m, times x. So there's this maximum acceleration, minimum acceleration. It's sort of the flipped of the a. Sorry, a is the flipped of the x, just like this equation shows. So if we were going to try to draw it, which I'll try to do here, if we want to do, let's use blue for x versus time. It's good to try to sketch this yourself. If it starts at this, it starts at A, it'll go down to here to negative A, and then back up. So I encourage you to try this, actually draw it. Something like that, okay? So I'm not doing it very well, but you got the idea. So then if we want to do, let's do green for velocity, V, versus t. What that's going to do is, look, it starts at 0. You release it from rest. But then it starts, remember, this is the slope, right? It goes to negative slope. And then the maximum slope is right here. So the maximum like negativeness velocity is right there. And then it stops right here. So this is v equals 0, right? The slope is 0 right there. So this is when it comes back to here. And then it's got maximum positive slope right here. So it goes up until it gets to there. And then again, 0 slope up there, so it goes down to here. I'm not very good at drawing this, but you're hopefully getting the idea. Maximum negative slope is here. Goes to 0 again right here. And then maximum positive slope right there. Okay. And what this is, I just call this V max. I haven't given you an equation for that yet. And negative V max, I guess. Sorry, it's so messy. To get the right idea, right? The amplitude is just simply like the maximum x. A is equal to maximum x value away from equilibrium. Maybe I'll put that here. So A equals x max. It's called the amplitude in meters. And remember, this is, sorry, that's the equation right there that we're graphing. And then the last thing, maybe I'll put it in orange or something, is A versus time, so you can see that. So it starts off at negative slope, so the maximum negative acceleration is right there. Then there's a 0 slope up here, so it passes through 0. Then it's maximum positive slope right there, so it gets up to the maximum. Then it's 0 right there. And then it's maximum negative slope right there. Got it? 0 right, oops, 0 right there, so it comes to 0. Maximum positive slope right there. And then back to 0 slope right there. Okay. And as you can see, I've just done the slope of the slope of the slope. The way it all works out is that when you have a sine curve like this, the acceleration graph is flipped of the A graph. Hopefully you had a chance to actually try to sketch that on a piece of paper. Tang, did you want to unmute?
Hello, Prof. Harlow.
Hi.
I'm a little bit confused with what you had said about using either sine or cosine.
Yeah.
So is there any way, like when are we allowed to use sine? Is it when x equals to 0 and t also equals to 0?
Right, exactly. So this is all about the initial conditions. So I have, when you draw this x equals a times cosine of something times t, if you do t equals 0, you always get that x equals a, right? So you say that it was released from rest. Also, the velocity is going to be 0 because there's another equation for velocity there. But so you release it from rest, that puts it at a certain position. There's other ways to start simple harmonic motion. Maybe you start at equilibrium and give it a positive velocity, for example. And if you do that, that's when you can use this x equals a sine of 2 pi little t over t. Let's talk a little bit more about this. The period t is set by the properties of the system. In this case, of a mass m attached to a spring constant k, the period is always this equation. T is equal to 2 pi times the square root of m over k. But A, the amplitude, is set by the initial conditions. Whatever your initial x value was and your initial v value was, that's going to determine what the A is. So it's sort of two different things here. There's the properties of the system, like how much does it weigh, how stiff is the spring, you can't really change those. And then there's the initial conditions, which is, did you kick it? Did you drop it on the floor? Did it start with some velocity? You know, what did you do to it to get it going, to get it started? Okay. So let's do a quick poll question, see if we're following this. Which of the two constants, A and T. So there's these two constants in this equation. So you got X as a function of little t, right? 2 and pi are constants, obviously. A and T are new constants. So which are determined by the initial position and velocity of the mass? Is it only the amplitude, A? Is it only the period, T? Are they both determined by the initial position and velocity, or are neither of them determined by the initial period and velocity? Another way of putting it is like X is the dependent variable. Right? And T is the independent variable. And A and T are constants of motion. Okay, please click into the poll. You got a good answer for that. 3, 2, 1. Right. So only the amplitude is determined by the initial conditions, because the period must be equal to 2 pi times the square root of m over k. Okay. This is the mass, and the mass is a property, an unchanging property of the system. And the spring constant, it's whatever spring you happen to buy, right? Doesn't matter how you kick it or how you get it started. The period's the period. So that's on the next slide. The period is set by the properties of the system. In the case of a mass m attached to a spring constant k, the period is always this value. And the amplitude, though, is set by whatever your initial conditions are. I think that's pretty much it. I could. Good questions here. Sunny, question?
Oh, hi, Professor.
Hi.
I actually have a question about regrading. It's not about the content you just covered.
Okay.
So I was wondering if we can only request a regrading for just one of the questions, if we have just questions on just one of the problems.
What, you don't want me to look at the other one?
Oh, no, it's just that I had specific questions about just one of the problems, so I was wondering if I could.
That's absolutely fine. What I'm just saying is that I'm reserving the right. If I'm re-looking at your test, I think I should be allowed to look at both the questions, shouldn't I?
Oh yeah, I was just wondering if I should specify which question.
Yeah, that's helpful. Yeah, to specify okay. When you send the email, just let me know what you thought went wrong there.
Yeah, that was my question.
Yeah, okay. Good. And then Munitha.
Hi, Professor. I had a more general question also that was actually kind of looking forward to our final exam.
Yes.
So I was wondering that normally when we're studying for specific tests, we have more time, and so we can cover more content and we can go through everything thoroughly. So, but how would you suggest we study for the final exam? Like, what do you think we should focus on more so the lecture content that we did in class together, the slides, the concepts covered, the calculation questions that we did together, or more on the mastering physics content for practice?
Well, I mean, everything, both are kind of testable, right? The mastering physics stuff that you did, I'm going to be drawing from that. And, these kinds of questions from in class, I'm going to be drawing from that as well. It is a big course and there's a lot of content there. And, none of these questions on any of these tests you're going to have seen exactly before. It's these skills and concepts that you've learned that are going to help you be able to solve it day of, right?
Okay, got it. So we should just practice by, is there should we focus on one more than the other or anything like that?
Yeah, I guess maybe the lecture notes more I draw from than the mastering physics, but I mean, both are important though.
Okay, got it.
I would start with the lectures. And then Vanessa also asked on the chat, will there be lab questions on the final two? That's a good question. So I've actually asked the TAs and Professor Seelfin to come up with a question for both midterm 5 and also the final exam, a lab question for both. in multiple choice format. So let me just, I will go to these hands, but let me just sign off. Maybe I'll turn off the recording for you YouTube folks. I would like you to continue on with dynamics of simple harmonic motion. We've started in on that, but we're going to talk about the vertical spring and things like that. Energy in simple harmonic motion, that's a really interesting thing when you plot the potential energy of the spring as well as the kinetic energy of the mass versus time. And then we're going to talk about the simple pendulum, which is a whole other example also which follows simple harmonic motion. And don't forget, there will be a team up quiz that is going to happen on Friday as well. So please make a plan to meet up with your practicals lab partners in your Microsoft Teams and go on there and do the team up quiz right in the middle of lecture. And I think it's a fun way to, and there's going to be a little vote on your favorite TV show as well. So it's a good time to chat with your friends. So I'm going to turn off the recording and then I'll go to the hands.